Welcome in 3TR4 Lab 2. In this experiment we are going to have a double sideband suppressed carrier modulation circuit. We'll have this port for double sideband suppressed modulation. We'll use our function generator as a function as our carrier input, and we will drive the message from it. This is our power supply, and we'll show the time and frequency domains before modulation and after modulation. Our board starts from here. This is the power supply, as I said. This is your input function generator. We have input frequency at 64 kilohertz. This is our carrier frequency. It is sinusoidal. Amplitude 10 volt peak to peak. There is no offset or cycle. This signal comes here. It is still 64 kilohertz. So what we are going to do, this is the block diagram of our board. This is the input 64 kilohertz, 10 volt peak to peak sinusoidal. We'll input it to a circuit, Schmidt-Trigger circuit, which instead of 64 kilohertz sinusoidal, it outputs the same circuit, the same output, but instead of sinusoidal, it is a square wave. What is the advantage of having a square wave? It is easy to divide. Just a divide by 16 counter. Instead of 64 kilohertz, divide by 16, we have 4 kilohertz square wave. As you know from lab 1, if you have a periodic signal, 4 kilohertz signal, then actually it will appear in frequency domain at 4 kilohertz, 8 kilohertz, 12 kilohertz, and at 4 kilohertz, and it's fundamental. Using low pass filter, low pass Butterworth cutoff filter 4 kilohertz, I could only get the 4 kilohertz and get a sinusoidal wave from this. So from the carrier, we transfer it to square wave. From a square wave, we divide it by 16 and back to a sinusoidal wave. So we have two waves, the carrier wave, which is 64 sinusoidal, and the message which is 4 kilohertz sinusoidal. How to look at this? If you looked here, you will find TP1. It is test point 1. Test point 1, so you could use your oscilloscope to look at it to look at the signal at this point. This is my board. Let's start looking. This is our board, so this is your input. This is your input signal from here. It starts processing, Schmidt-Trigger, and division. You have test point 1 here, this point. Don't miss to connect the ground down. So this is your test point. Let's see. This is the yellow one. Let's auto scale. Okay, so this is now our square wave signal. Our square wave signal, let's check. Let's check the frequency. If we look at these two cursors, the difference here is 4 kilohertz. So we have from the 64 kilohertz input, we get our 4 kilohertz square wave. This square wave, as we know, we already know from part 1, it has a Fourier series because it's periodic. It's at Fourier series. It appears at 4 kilohertz, 8 kilohertz, 12, and so on till infinity. If I have a low pass filter, if I have a good low pass filter, I could get the 4 kilohertz only and dismiss all others. So I take the 4 kilohertz only and get a sine wave from the 4 kilohertz. I could look at this at test point 2. Start looking here. Let's auto scale again. Okay, so the same signal, the same square wave, I got a sinusoidal from it, just a low pass filter. So from my carrier, I got my message. What we do in double sideband suppressed carrier, just multiply both to each other. What we do when we make amplitude modulation, or if we send the carrier, we multiply the message to the carrier and add the carrier. So if we have my message, it has some frequency band here. When I multiply by the carrier, the same components appear around the carrier away from the 0. This is the baseband 0. This is 0. So my message, instead of being at baseband, it is now at passband here and here. My message in this case is a 4 kilohertz. So it appears at 4 kilohertz here and minus 4 kilohertz here. Multiplied by my carrier is 64 kilohertz. So my message appear before 64 by 4K, so it is appears at 60K and 68K. And of course on the negative frequency as it is. So I don't have all this, I just have 4 kilohertz component here and negative 4 components kilohertz here. So when multiplied by 64 appears at 60 and 68. When multiplied again by cosine omega ct, these components again transform to the base, to the baseband, so I can use a low pass filter to get back my message again. This is ideally. This is what we say in the lectures. Practically, there is a lot of problems. Life is not easy in practice. Ideally, I just multiply by cosine omega ct in the transmitter and everything is okay. And in the receiver and multiply again by cosine omega ct and everything is okay. Practically, when I multiply by cosine omega ct, there is always a leakage. The multiplier actually is not linear. When you get your m of t multiplied by cosine omega ct, you don't get m of t multiplied by cosine omega t only. You get other terms which is the cosine omega ct, and sometimes it's harmonics. Instead of only of the 64 kilohertz, you get its harmonics. 64 kilohertz, 128 kilohertz, you have your signal plus extra signals which are called harmonics, which are not your signals or your intended signals. This distorts your signal. In the receiver, again, you multiply by 64 kilohertz. You hope that the 64 kilohertz multiplied by 64 kilohertz and the low-pass filter will make your life very easy. Again, multiplication again will make extra leaks. You'll have your signal plus extra signals at 64 kilohertz, extra signals at 128 kilohertz. Even if you have a good low-pass filter, there will be some components, some traces of these components making your signal somewhat noisy. We look at this in time domains and frequency domains and look again how is this going. Okay, so now we have a TP1, test point 1 and test point 2. We have our square wave, which is 4 kilohertz. We are ready now with our 4 kilohertz sinusoidal message. The level of your message, if you look at PT1, it is a potentiometer 1. Potentiometer 1, as you know, it is a variable resistance. It changes the amplitude of your signal, of your message. To be clear, it changes the amplitude of your message. No problem. So as I change the potentiometer, the amplitude of my message changes. Okay. Now let's look after the modulation. So this is the input square wave. This is my sinusoidal. This is my sinusoidal message. Let's see after the multiplication. Let's go now and see what happens after the multiplication in test point 3. Let's again use odd scale. As you can see, this is my message. Still, I'm connecting my message to test point 2. At test point 3, as you look here, you have the carrier, which is the yellow fast one, and there is the envelope, which is the borders. If I move on the borders of this wave, if I move on the edges of this wave, it is the same as my wave. You know from the theory part, if I have m of t, which is my message, assume it something like this, something random. When multiplied by cosine omega ct, what happens? The carrier is multiplied again inside this. We just make the same message as if it is mirrored and just plotting our carrier, right? We just fill the spaces with our carrier like this. What if my message is shifted? If I have some constant added to my message to make it all positive. Now my message, as if my message is like this. When multiplied by the carrier, again, I'll draw the same signal as like this. So I'll have my carrier like this. Sorry for my bad drawing. Okay, so the edges of my carrier are my message, and the carrier itself is the fast varying one here. So my message here is this slowly varying sine wave, 4 kilohertz. The yellow one is the fast varying carrier, 64 kilohertz, and the envelope of this carrier is my message. the envelope, the shape of this carrier is my message. If we make it, look, as if every my message it is this, the part on the amplitude of the carrier. If we could even cancel this, hope it is better now. Not better at all. Okay. Oh, sorry, this is cursor. Okay. Let's now change potentiometer 2. Potentiometer 2 changes this constant. We said that we having our message added to a constant, then multiplied by the carrier. This constant must be big enough so that all the messages become positive. If it is not a big number, some of the message will be positive, some of the message will be negative, and we'll have this crossover point. My message will reach 0 at some point, so 0 multiplied by the carrier, we'll have always 0. So we have now no zeros because the message plus a number is a big number. If we change if we decrease the constant like this, we have 0 points. If we changed it again, changed it to a big number, we have no 0 points. So when we change, there is 0 intersection, like this. Okay, if there is some benefit of adding a constant to my message before multiplying to the carrier, is there a benefit of making my message all positive? Yes, there is an easy to implement detection circuits. If your message is all positive, there is very easy detection circuits, mainly called envelope detectors, could detect your message with very cheap prices. If not this constant is taken, your message only m of t multiplied by cosine omega ct, you need to multiply in the receiver by cosine omega ct again, which need expensive equipments to have a synchronized carrier with the transmitter. But with this constant, you could use envelope detectors, which works well without synchronization, which is cheap as well. Okay, so this is our message multiplied by the carrier. Now, TP4 is after, this is the receiver part, after multiplying the carrier again, and TP5 is after the low-pass filtering. Let's see 4 and 5 and see why they are not good as we expect. Let's again auto scale. Not good at all, right? We could try to make it slightly better. This is TP4. We have our sine wave, as we see. It is good, but with very sharp edges, right? This is sharp edges, many sharp edges. Why there is sharp edges? This is before the filtering, right? So we have our m of t multiplied by cosine omega ct. This is for the transmitter, and in the receiver it is multiplied again by cosine omega ct. Cosine multiplied by cosine, it is cosine squared, which could be written as cosine 1 plus cosine 2 omega ct. This is my message, which is good, but I have another component which is cosine 2 omega ct, which is a very high frequency component, right? Omega ct is 64 kilohertz, 2 omega ct it is frequency 128 kilohertz. That's what's making sharp edges everywhere like this. Okay, I'm trying now to filter this to get my message, but my message is not clear, as we see here. This is not the sinusoidal we have input. We have a good input sinusoidal wave, but this is not clearly an input sinusoidal wave. So let's go to the frequency domain and see why it is not that good. Again, frequency domain, so we want math. FFT operation will operate on source 1, the yellow signal. We'll make the span 200 kilohertz. Center, we are at baseband signal. We make center 0. Okay. Here we have the answer. I don't want signals now. Give me the cursors. This is my first cursor. If I'm here, that's my 4 kilohertz signal. As you see, it is a big peak. The peak here has a good amplitude. That's very fine, but it is not alone. there is another peak here. What is this peak for? It is the 64 kilohertz. It is not, I used a low-pass filter, but the low-pass filter is not 100% idle. As you see, there is a considerable amount of the 64 kilohertz carrier still in the circuit. This 64 kilohertz make my signal noisy. Even if I could change the span a bit more, oh, it is the 64 kilohertz. There is a more important one at the 128 kilohertz. Look, very bad amplitude. There is again at the third harmonic. So the carrier itself and its harmonic are actually destroying our signal. By potentiometer 3, PT3, which is located here, we are trying to make things better. We are trying to minimize the peaks. We're trying to minimize the carrier peaks. But in the cases, this is a practical filter. It is actually a weak practical filter. There is much better, more filters than this. But in the end, it will leaks. It will give me 64 kilohertz components, 128 kilohertz components. These components are destroying my signal. If I want a better one, I must use a better worth of much higher order to suppress these extra components which are destroying my signal or making it very noisy. Okay, so I have a 4 kilohertz signal multiplied by carrier. I am now in the frequency domain. This signal multiplied again by cosine omega ct, I am back to the baseband. But I am not alone in the baseband. I have the carrier, its harmonics. These harmonics, yes, they are. I removed a good portion of their energy with the filter, but there is a considerable part of their energy destroying my signal. If I want a better one, I must use a much better filter. Okay. Let's see the filter response. So this is the filter of the output. So now we know why the output is bad like this. So for the input, what is the filter? What is the spectrum of the input? Which is TP3. This is the modulated input. Oh, sorry. Let's take this one because it is the one connected to the FFT now. Okay. Let's make the center the 64 kilohertz. Okay, let's decrease the span first. Okay. Not working yet. Span. Oh, this is 60 hertz, sorry. We want 64 kilohertz. 64. Okay, let's decrease the span a bit. Okay, let's see with the cursors what do I have. This is the 64 kilohertz. Oh, so first of all, this is the amplitude of my carrier. My message is very near. Actually, you could hardly see the amplitude. It is here. It is 4 kilohertz before and 4 kilohertz after. So if I'm here at 68, you could see the amplitude now. It appears, but it is not. It's not so obvious. Or at 60 or at 60 kilohertz. Okay, let's try to make it more obvious. How to make it more obvious? Just decrease the amplitude of the carrier. I've just decreased the amplitude of the carrier. As we see, the carrier level now is less. Let's decrease a bit more. So, as you see here, the carrier amplitude is less and the message are more clear now. Okay, so this is my message, but as you see, my message here appears in the, yes, it is appears my 60 kilohertz and 68 kilohertz, but still there is some noise because my input signal was actually square wave. I filtered it using an idle filter, which didn't get rid of all components. So I have high noise actually in the background. If I am back again using this, so I'm getting back my carrier here again. I'm getting a more carrier here, or I'll just decrease the carrier. Okay, this I suppress the carrier now. So to summarize what we are going to do here, we have a double sideband suppressed carrier signal. We have an input 64 kilohertz signal. The 64 kilohertz signal by comparator, I change it to square wave of 64 kilohertz signal, divide by 16, and I get my square wave 4 kilohertz signal. This signal I make a low pass filter to get a 4 kilohertz sinusoidal. The amplitude of this sinusoidal is controlled by TP1, which is potentiometer. Sorry, it is controlled by potentiometer 1, and could be seen in TP2. For my carrier, I could control the amplitude of the carrier here. The amplitude of carrier, I mean the constant beside the message, which is multiplied by the carrier, as if it is the DC offset of the message. Using this DC offset, as I said before, makes the signal all positive, which allows us to use very cheap demodulation circuits. Here we have the modulated signal. We saw it in time domain, we saw it in frequency domain. As we see in frequency domain, we have two peaks for the message and the peak for the carrier. For TP4 and TP5, it is the signal multiplied again by cosine omega CT in the receiver part and after the filter. As we see, the filter is not idle, so we have, yes, our message, but we have some components, some leaking components from the 64 kilohertz and its harmonic, not 64 only, but 64 and 128 kilohertz. These harmonics should be suppressed by using a better filter to get a good output and to get back your signal. You could adjust potentiometer 3 to make these peaks, which are the 64 and 128, as minimum as possible. As you vary this, you try to suppress these peaks as much as you can. In this lab, there is a pre-lab exercises. Actually, you are going to write your report before you come to the lab. You just move on these parts, try to make all this, try to write the MATLAB codes, get your outputs, get everything, compare this to those of the video according to my explanation now. You'll hand in your second report in lab 2. So you'll prepare most of the report before the lab. If there is something, small points you want to check by using the oscilloscope, or just check by using maybe a function generator, or even asking us, just leave some small space to write it down. And in the end of the lab, you'll have your report ready. Okay, that's it.